Hello and welcome to Maths with Mr Amison. In this video I'm going to be going through how to calculate experimental probabilities and use them to predict what we might expect in certain events. If you need to recap this topic, then please watch Mr Chowdhury's video. I'm going to start by showing you an example, talking through it, then giving you time to copy it down and have a go yourself. Feel free to pause at any time. So in this example you can see we have 7 blue and 3 red cars that passed a house, and therefore you can see the experimental probability, which is basically the probability of seeing a red based on that experiment, because there's no theoretical probability of seeing a red car pass the house, it's just chance. But the experimental probability based on what was seen, 3 red cars out of 10 cars in total. Therefore, the experimental probability is 3/10, which we can write as 0.3. If 200 passed the house, how many times would we expect to see a red car? Well, if 3/10 or 0.3 of the cars were red, then we would expect 3/10 of the 200 cars to also be red. So if we multiply by the 0.3 or by 3/10, we find 3/10 of 200. And therefore we should expect to see 60 red cars. Now if we want to explain how we can make this experimental probability more accurate, then really what we need to do is we need to increase the number of trials. Whenever we have experimental probability and we're trying to make it more accurate, that is the thing we need to do. In this case, the number of trials is the number of cars that we see. So if we watch for longer and see more cars, we'd have a bigger sample size, which would mean the experimental probability that we get would be more accurate. The more cars that we see, the more likely those cars represent the general colour of cars in the population. Now, it doesn't necessarily mean it's totally true, because it might be that more red cars pass on certain days, but it gives an indication. This is why we only say what we would expect to see if 200 passed the house, not what we definitely would see. Okay, so make sure you copy that down and have a go at the question on the right. Now you've had a chance to have a go, then let's go through this question. So if 20 cars pass a house, 6 were blue, 14 were red, we want the experimental probability of seeing a red car. That's 14 out of 20, so 0.7. If 200 passed the house, how many times would we expect to see a blue car? Well, the probability of a blue car was 0.3 in this case, because we had a probability of 0.7 seeing a red, because there are only red and blue cars. So if we multiply the 200 by 0.3, which is the experimental probability for the blue, then we should get 60, so we expect to see 60 blue cars. 25 cars passed a house on Tuesday morning, and the experimental probability from this example was 0.6. Which experimental probability is more accurate, the 0.6 from the 25 or the 0.7 from the 20? Well, in fact, it is the 0.6, because we saw more cars on Tuesday, therefore that experimental probability is more likely to represent the actual spread of different colour cars in the population rather than the 20 cars. The more trials there are, the more accurate the experimental probability. And that's important to recognise. Alright? What we could have done is we could have added the total number of cars seen together, the total number of cars altogether, and the total number of blue cars and the total number of red cars, added them all together, and then we'd have got an even more accurate experimental probability. Okay, so here are 6 questions for you to try. See if you can answer each of them. They do get more difficult towards the end, and you are required to write some explanations. It's worth taking time to write this down on some paper rather than just trying to do these in your head. Have a go. So here are the answers to these questions. Question 1, 42 out of 50 grew, so the experimental probability is 42 over 50. Question 2, 80% is the experimental probability of passing a certain maths test. If 50 took the test, how many would we expect to fail? So if 80% of 50 are going to pass, that's 40. If 50 took the test altogether, that means 10 are going to fail. Question 3, 30 people saw the latest film at 10 AM, 9 didn't like it. If 50 people went to see it at 11 AM, well, how many would we expect not to like it? So 9 out of 30 didn't like it, so the experimental probability is 9 over 30. And we can multiply that by the number of people that went to see it at 11 AM. So multiply it by 50. Now I've simplified the fraction 9/30ths to 3/10, just to make the question a little bit easier to do it without, to show you can do this without a calculator. And then the numerator of the fraction multiplied by the integer. So 3 times 50 is 150 over 10. Which is 15. So we might expect 15 people not to like the film at 11 AM. If Sam asked 10 people if they had a pet, 70% of them did. It might not be very accurate because it's a small sample. 10 people is not many people and might not represent the population very well. Question 5, 92 football matches. A certain player scored in 23 of them. In the next 8 matches, that player doesn't score. Well, that means there's been 100 games in total, and they only scored in 23 of them. So 23 out of 100, 23 over 100 is their experimental probability of scoring in a game. For question 6, if we have X oranges in a bag and 3 were mouldy, and in a second bag of the same amount of oranges, 5 were mouldy, that means 8 out of 2x oranges in total were mouldy. If we have 200 oranges, and if I tell you that we expect 40 to be mouldy, that means 8 out of 2x will be the same as 40 out of 200 as equivalent fractions. If we change the fraction on the left by multiplying the numerator and denominator by 5, we get 40 over 10x. So 40 over 10x will be the same as 40 over 200. You can see clearly there that 10x is equal to 200. X would have to be 20 because 10 times 20 is 200. Okay? So I hope you found that useful. Some of those questions towards the end were rather complicated, and I understand if you struggled with it. But keep trying, keep working hard. Bye for now.